inverse iteration method was cooked up by my colleague Gabor Vatai while he was doing cycle expansions and stuff. And the idea is this. I have some theory, what in our parlance is called a scalar field theory, which means I have some theory which is described by some kind of potential or something, and it's described by differences with the neighbors, Laplacians or similar stuff. And that's, vaguely speaking, the kinetic term and potential, but have to be careful because we are not separating time as a special coordinate. It's just the structure of the theory. So the structure of the theory that locally, I look at the lattice site T. What I do at this lattice site, I take this field and I say, well, I have to square it and I have to stretch it. So that's what happens locally. And then I have to look at my neighbors to the left or right, or in this case, you can think before me or after me. And I want to compare these ones. And I'm given a command from the Generalissimo saying that that thing has to be something I'll call forcing term. Now in Bernoulli cat map, these are all integers and everybody was integer. There was some integer and it could be interpreted as a symbol for a particular, state. But what it really was, it's something that's dimensional at the same dimension as the field, just looking at the sum. And what it really is, it's some kind of translation in the field values because, it's being added up to these things. Now, the principle of what in Denmark and Scandinavia is called Jentaloven, which means we all have to be equal or nobody should stick out, is to say, it's a little bit difficult because this one is hyperactive person here. So he can do some crazy stuff, but it has to follow the law. And that means that if I take the source term and all the neighbors, in this case, the only two, but there could be any number. And if I now divide everything by a, so I get 5t squared on this side, and take a square root because, to get the size of the field, I have to take square root. I get a formula which any solution, anybody who is obeying the law should exactly satisfy. Now here, I have to choose two signs taking the square, and I can call this symbolic dynamics in this case. And this sign in our very simple example. So let me remind you what this anon looks like. So phi cube field theory has a small horseshoe, surprisingly, but I didn't expect this myself from field theories. But that's what it has. And the way to see it, the way that we find it convenient to visualize it, is that if you look on a plane, we have a second order difference equation. So we have to specify initial condition for which is specifying two lattice sites. Phi t convenient thing is to look at two consecutive lattice sites. We can immediately do a calculation saying that on the diagonal, we'll have solutions which we call fixed points or constant solutions. I'll put a little hat to bar to signify them. So if I set, and that's true for any field theory, but here it's particularly simple. If I set the same field every place, I look at my law, says I look to the left, it's same. I look to the right, it's same. But at my site, I have to stretch out by a square and by a constant. And this now has to be same as the source, but there'll be some single source term. This turns out to be a simple quadratic equation which has two parameters. It has a source term and this A. But we worked it out and we find out that there are two fixed points. One is here, one is there. So again, these are fields, these are not some kind of coordinates. And these fixed points, they have names. So this one, conventional called phi 0. In our conventions, other people can do other stuff. There are two of them. Plot out stable and unstable manifolds because we know that's what we have to always do. It turns out that unstable manifold of this guy goes like that. So unstable, I go out, stable, I go in. Now, if I go a little bit further out, because of this squaring, but that's actually why we have this square, we are bounded in maximal value. The unstable manifold has to bend down, re-enter someplace here. And when I look at the stable manifold, that does the same kind of thing, goes out and re-enters. And I find nice area where I know that everybody outside the unstable manifold runs away toward the infinity. Now, stable and unstable manifolds only differ by time reversal. So anybody on this side of the stable manifold is somebody who started at infinity and has approached the stable manifold. So I know that everybody outside of this diamond is guaranteed to be a stranger because they came from someplace or they're going someplace. They will not stay forever as a non-wandering set. That's all in this bounded region. And there are two fixed points in this region. Now I do iteration of this diamond once forward in time. The fixed points, they stay, they never go anyplace. So this guy and this guy, they stay. But this whole area, if you're on a stable, unstable manifold, you have to stay on it. So this point has to go closer, let's call it D. So around the stable, unstable manifolds, this point comes in closer. So this whole region gets stretched. This edge gets to be very thin. D ends up here. This gets stretched out, kind of re-enters. And I end up with two regions in which I can still have non-wandering set. But in the second iteration, everybody who is outside of these borders, belongs to this strange world of sites. So everybody out there is there. Now, the reason why I'm doing is I'm telling you now that I know for the sufficiently strong coupling, sufficiently strong A in these formulas, I know that I have two regions which are very distinct. You know, this is 0. So everybody here has positive, and everybody in this region has negative. And this is the rationale why Vata in his method has sigma t, a sign which is +1 or -1, depending whether the value of my field that I start, I'm trying to gain is someplace in this region or that region. So I have very clearly separated. And now I can use this method to improve if I don't have, correct. So suppose I started with fields which I thought were pretty good. So here is a latticide T, latticide T +1, latticide T -1. And I made some kind of guess what these fields should look like. And to indicate the guess fields, I give them a name. So here, my first 0th order guess is this, maybe. And if I keep iterating this procedure, whenever I have a mth guess, I use this to find the correction to make these guys better obeying the law. There's a square root here in this particular case, in Vata method. So that's the meaning of the method. I get a correction because I penalize. There is, I was sticking out. People on Baidu immediately noticed this, and the neighbors told me, "You can't say this. Get down." And that's what inverse iteration method is doing. It's producing corrections, and the way it does is that I check everybody on a finite lattice of n sides. So, this starts as 0, ends at n -1, these lattice sides, and then it repeats itself. So I only have to do it in one period of the lattice. And what the method does is I have the whole approximate lattice configuration, not lattice state, which is supposed to be the solution of this procedure. I have a approximate lattice configuration. From it, I improve every side by computing this neighborhood thing and every lattice side, and then I get an improved state, and I keep doing it, wash and repeat, until I get it to the accuracy that I want. The main idea here is that I know that non-wandering set that I'm interested in has clearly demarcated regions in it, and I can give them a name, and I can use that information to construct a guess. So the values of this thing, if you think that there was evolution in time, they're called itinerary. The values of these signs here, +/-1. But if you think of this as a lattice, it's just a lattice. There is no direction of time. It's not a time, but it's the way to solve something globally. And what you're implicitly using when you get to the end of, you're using periodicity to know that your neighbor is on this side when I'm on that side. So that's essential part of this calculation. And that's inverse iteration method. Now, this was designed for anon, thinking about 5-4 theory, which has a cube here. So am I supposed to take a cubic root? I don't think so. The essential thing to take out what we have learned, call it shadowing method.